All right, welcome back. Today, we're going to jump into a concept that is, it's really the foundation for just about every field of engineering, mathematical modeling. And we're going to use a pretty cool example, a bungee jumper, to uncover a really powerful universal law of conservation. So you ready? Let's get into it.
Okay, so imagine this. It's your first day at a new engineering job. Your boss comes to you and says, "We need you to predict a bungee jumper's velocity to make sure everything's safe." So where do you even start? This is not just some problem in a textbook, right? This is the kind of real-world challenge engineers have to solve all the time, taking something that seems complex and messy and making it predictable.
So how do we begin? Well, we start by building a model. What we have to do is translate the actual physics of a person falling through the air into the language of mathematics. This is always the crucial first step for any engineering problem.
Now, the key phrase here is essential features. See, a model isn't a perfect one-to-one copy of reality. It can't be. It's a simplification. We have to intentionally ignore the minor stuff, like the direction of the wind that day or what the jumper ate for lunch, so we can focus on the big, important forces that are really driving the whole thing. The goal is to capture the essence of the system in an equation we can actually solve. So for our bungee jumper, the essential features are actually pretty straightforward. You've got gravity pulling them down, and you've got air resistance pushing them up. That's it. That's the core of the problem. The jumper's entire motion is basically a tug-of-war between these two opposing forces. And here's how we turn that physical tug-of-war into a mathematical equation. We start with a classic, a cornerstone of physics, Newton's second law. Then we define our net force, F, as the downward force of gravity minus that upward force from air resistance, which, by the way, gets stronger the faster the jumper falls. We put all of that together, and voila, we get this, a differential equation. Now, don't let that term dv/dt throw you. All it means is the rate of change of velocity. In other words, it's just a fancy way of saying acceleration. This single equation right here, that's our complete mathematical model for the falling jumper. Okay, so we've built our model. That's a huge step. But an equation itself isn't the final answer, right? It's just the roadmap. Now we have to actually solve it to find that velocity we were hired to predict in the first place. Let's take a look at how we can use that. So in engineering, there are usually two main ways to crack a problem like this. On one hand, you've got the analytical solution. This uses some pretty advanced calculus to come up with one single, perfect formula that gives you the exact velocity at any moment in time. Then on the other hand, you have the numerical solution. This approach uses simple arithmetic to calculate the velocity in little chunks, in discrete steps, like what's the velocity every 2 seconds. It's an approximation for sure, but it's incredibly powerful because this is exactly how computers are designed to solve these kinds of problems. And this little expression right here, this is the heart and soul of the numerical method. It's often called Euler's method. It's so simple but so clever. You just take the velocity you have right now, that's your old value, you calculate how fast it's changing, that's your slope, and you use that to predict the new value a tiny step forward in time, and then you just do it again and again and again. And here's what that looks like in action. We start at time 0, obviously with 0 velocity. We run the calculation, and we find the velocity at 2 seconds is 19.62. Now we use that value as our new old value to find the velocity at 4 seconds, and so on. But notice something interesting here. Look at the numbers. The velocity isn't increasing by the same amount each time. The jumper is still accelerating, but that acceleration is definitely slowing down. So what does that changing acceleration really tell us about what's going on with the jumper? Well, the solution reveals that there are two very distinct phases to the jumper's fall, and these are absolutely crucial concepts in all of engineering.
Now, when we plot the velocity over time, and this chart is using that perfect analytical solution we talked about, a really clear pattern just pops right out. You can see the super rapid increase in speed at the beginning, but then it starts to slow down, and the velocity begins to level off as it gets closer and closer to what we call terminal velocity.
This graph isn't just a curve. It's actually telling a story. It's the story of a system that's moving from a state of really rapid change, where all the forces are unbalanced, to a state of equilibrium, where those forces have finally found a balance.
So here's the big idea. We call that first period, the one with all the acceleration, the transient state. This is when things are actively changing from moment to moment. But eventually, that upward force of air resistance grows and grows until it perfectly matches the downward force of gravity. At that point, the net force is 0. The jumper stops accelerating. The system has reached its steady state.
Okay, now let's zoom out. This whole idea of a system moving from a transient to a steady state, well, that's not just for bungee jumpers. It is a fundamental principle that governs countless systems all across science and engineering.
And this is it. This is the big one, the universal conservation law. I know it looks incredibly simple, right? But this one little relationship is the foundation for almost everything we model as engineers. The change in any quantity in a system, any quantity at all, is simply what's being added minus what's being taken away.
And this law perfectly describes what happened to our bungee jumper. During that transient phase, the increases in velocity from gravity were way bigger than the decreases from air resistance. So there was a net change, acceleration. But at steady state, those forces balanced out. The increases equaled the decreases, so the net change became zero, no more acceleration.
Let's use another quick example to really nail this down. Think about water flowing through some pipes. If the system is in a steady state, then at any junction, the total amount of water flowing in has to equal the total amount flowing out. So if you have 180 units coming in, you have to have 180 units going out. Increases equal decreases. It's the exact same principle, just applied to fluid dynamics instead of forces.
And that is the absolute key takeaway. Whether you are balancing forces on a falling object, balancing mass in a chemical reactor, current in an electrical circuit, or heat in a car engine, you are using this exact same fundamental conservation law. The specific details and the variables change, but the core mathematical idea, it stays exactly the same.
So as an engineer, this becomes one of the very first questions you ask when you look at any system. Is it changing or is it in balance? Is it in a transient state or is it reached a steady state? Understanding that distinction is absolutely fundamental to modeling almost anything. It's the question that really opens the door to understanding the world around us in a much deeper and much more predictable way.